So 1.2 is a slight distraction. It's not that useful. I believe they do it because there's some applications in biology, especially medicine, that look at absolute value. So looking at the absolute value graph, you would see the parent function. The graph would look something like this. And what's interesting is the right side is usually an exact mirror of the left side. And that makes sense because if you think about it, all that's happening is for all the values of x that are negative over here, you're making the y value the same y value as over here. So if it's 3 or minus 3 for x, the y value is still going to be 3 and positive 3. So it makes sense, which means that wherever the vertex is, the distance to the x value is always going to be the same, and it's always going to be represented as an absolute value. Now this section looks at blood pressure, and blood pressure says that anything at 120 for your systolic, I think it is normal. And anything above that by 20 or below that by 20 is considered dangerous, or at least looking into. So that means if 120 is right in the middle, as you stretch this way or this way, you're getting off track with your blood pressure. And I think that's why they look at this chapter. And let's look at two scenarios. Let's say you've got your number line here and you got 0 right in the middle. And you're trying to say, I'm looking at minus 3 here and positive 3 here, and I'm looking for all the x values that are above and equal and below or equal to minus 3. So above plus 3 and below minus 3. And that's very easy to write. You would just say all the x values are going to be, all the absolute values of x are going to be smaller, or sorry, bigger or equal to 3. Which, if we look at it, if I put 1 in here, it doesn't work. If I put minus 1 in there, it doesn't work. That's because 1 is not bigger and equal to 3. But as soon as I get, and the same with 2, if I put in 2 or minus 2, it becomes 2 is bigger or equal to 3, which is not true. But as soon as I get to the positive 3, positive 4, or negative 3, or negative 4, this becomes true. That's because at negative 3, it gets absolute value, becomes 3, is bigger or equal to 3, which is true. So that means that whenever we have 0 in the middle, that's the important part, and we're just saying, well, x is bigger or equal to 3, and then we just slam an absolute value on, and that will also account for smaller, when it's negative 3 or smaller. Slightly different case when we're looking at in between. When we're looking at in between, which means plus 3 all the way down to minus 3, so sort of inclusive, you would say that x is going to be smaller or equal to 3 on this side, and that minus 3 is smaller or equal to x on that side. So what you would do here is say the absolute value of x must be smaller or equal to 3. And so that works. See, when it's 4, nope, that doesn't work. When it's 3, that works. When it's 2, that works. When it's 1, that works. When it's minus 1, it becomes positive 1 with the absolute value. That works. When it's minus 2, that works. When it's minus 3, it still works. And when it's minus 4, it becomes positive 4 with the absolute value. It no longer works. So we can see that when we want it inclusive from minus 3 all the way to positive 3, instead of expressing it like this, we would express it like this. The absolute value of x is smaller than positive 3. And that includes this precisely. And as I just pointed out, when it's the number line but everywhere from -3 downwards and +3 upwards, its positive absolute value of x is bigger or equal to the number you're looking for. So that works when x is in the middle. When x is not in the middle, that doesn't work. So let's say you're looking for a range, and we're looking at 6 in the middle, and we're looking for anything up to 10 and anywhere down to 2. And we want it to be from 2 all the way up to +10 and including 2 and 10. Well, if I do x absolute value smaller and equal to 10, that doesn't work. 9, 8, 7, 6, 5, 4, 3, 2, 1. Those are all smaller or equal to 10, all the way down to -10. So that's way over here, but I don't want that. I want from 2 to 10. So in this case, you have to look at it like this way. You have to find out what your middle term is. What's your middle term? 6. And you have to say x minus 6, I think it's x minus 6, is smaller or equal to, and then you have to look at your range of distance you're looking for. 4. So let's look and see if that works. When x is positive 11, I get 11 minus 6. 5, is 5 smaller or equal to 4? No. When x is equal to 10, x minus 6, so 10 minus 6, 4. Absolute value of 4, is 4 smaller or equal to 4? Yes. 9, 9 minus 6 is 3. Absolute value of 3 is smaller than 4? Yeah. 6, so 6, I'm just jumping right to 6, minus 6 is 0. Is that smaller or equal to 4? Yeah, it is. 5 minus 1, is that minus 1's absolute value becomes 1, 1 smaller than 4. Let's just jump to 3. 3 minus 6, that's minus 3, absolute value is 3. Is 3 smaller or equal to 4? Yep. Is 2, 2 minus 6, minus 4, absolute value of minus 4 is 4. Is 4 smaller or equal to 1? 4? Yes. And then when we get to 1, 1 minus 6 is minus 5. Absolute value of minus 5 is plus 5. That is not smaller than equal to 1. So when we have a range in the middle that's not 0 when the middle's not 0, you just do x minus the 6 is smaller or equal to the distance, the gap between the two distances that you're looking at. So in this case, it's 4 to the 10 and 4 to the 2. So that's when you're trying to get between two numbers, and you got to use the middle point of those two numbers to express it as an absolute value. Works the same when you're going outside of that. So let's use a different middle point. Let's talk about 10, and we'll say 12 and 8, so a spread of 2. But we're going to say everything below 8 and including 8 and everything above 12 and including 12. Well, what's the gap? So it's x minus 10 and only absolute value. And this time we're going to say bigger or equal to, and what's our distance? 2. Let's try it out. 7. 7 minus 10 is minus 3. Absolute value is 3. Is 3 bigger or equal to 2? Yeah, it is. So is that in the range we want? Yeah, it is. Let's try 0 down here. 0 minus 10. Absolute value is minus 10. Absolute value of minus 10 is 10. Is 10 bigger or equal to 2? Yeah, it is. Let's try it right on our border. 8 minus 10 minus 2. Minus 2 absolute value is positive 2. Is positive 2 bigger or equal to 2? Yeah, it is. Now let's try a range we don't want. Let's just use 10. 10 minus 10 is 0. Absolute value is 0. 0 is 0 bigger or equal to 2? No, it isn't. Let's try 11. 11 minus 10 is 1. Is 1 bigger or equal to 2? No, it isn't. 12 minus 10 is 2. Is 2 bigger or equal to 2? Yes, it is. So you can see we use the bigger equal sign again for things that are outside the range. We're using x minus the middle term, and then we're using the 2 is the distance to either upper or bottom end of the scale. Fairly complicated, fairly useless, except for a few areas of medicine. It's any time you have a midpoint of something that's considered the optimum value, and anything on either side of it is worse than optimum value. So the big one I pointed out is blood pressure. They use that a lot for blood pressure. But let's look at some examples. So they don't, they just go right into the blood pressure as an example. They give you a couple readings. And they ask you to find the difference between those readings and perfect, which is 120. And then they ask you to graph it and find domain and range and whatever. And that's fine. I'm not going to go into it because it's not too big of a deal. But then they ask you to look at ranges where you're trying to write the range in terms of an absolute value. And they just get you used to absolute value first. So let's have a look at some of them. So in this case, a range in terms of lower to higher after it's been turned into absolute value. Okay, so obviously this becomes a positive 5. I'm not going to write positive because it all becomes positive. 15 and 12 and 25. So really you just got to look at the numbers inside the bracket without the minus and put it in the right order. So we're obviously going to go minus 5 absolute value, 12 absolute values next, 15 is next, absolute value of positive 20 is next, and absolute value of minus 25 is next. And those all just become 5, 12, 15, 20, and 25. What about this one? Evaluate. So this just wants you to get used to the complexities and just consider absolute value like a bracket in BEDMAS that you have to exercise first. So what's this? Absolute value of minus 22 plus 22. This one you have to do what's inside the bracket first. So minus 5 minus 13. That makes minus 18. And then you have to do absolute value of that, which becomes positive 18. I'm going in the wrong order, actually. I'll go down to B here. This says you got to do the absolute value of what's in the bracket first, so 35. And then you multiply it by minus 1 in front, so minus 35. You can see in this case, this negative is essentially turning any of the absolute values into a negative, sort of inverting the absolute value. And then D, you've got to subtract what's in the bracket first. You get minus 3, and what's the absolute value of minus 3? Plus 3. Then you've got to add it. What's minus 10 plus 2? It's minus 8. What's the absolute value of minus 8? 8. 3 plus 8, 11 is the answer, positive 11. So you see you got to evaluate what's inside the absolute value first like it's a bracket. What's up here? Well, you got to resolve this first. It comes positive 8 divided by minus 4, which becomes minus 2. These you have to resolve the division before you add them. So you get 22, positive 22 over positive 11, plus 16, plus minus 16, so let's just work out the minus 16 separately, divided by absolute value of minus 4, 4. So what's 22 divided by 11? It's 2. Plus, what's minus 16 divided by 4? It's minus 4. What's a plus minus? It's 2 minus 4. What's 2 minus 4? Minus 2. So the answer to that complicated one is minus 2. And you just got to resolve each thing in BEDMAS order before you ever add them. Express an absolute value notation. So in this case, it helps if you use your number line. So in this case, we're looking for something that's below minus 3 or above 3. And actually, we did that already. And so if you look at your number line, and it's below 3, minus 3, so it's not including 3. So it's everything over there and everything up here. And in this case, you just say absolute value of x is bigger than 3. And that'll work. Whatever number you put in there, even if it's minus 4, it will fit within this range here and this range here, and it will not include the 3 and not include the minus 3. Because when minus 3 is in there, it becomes 3. Is 3 bigger than 3? No. 3 is equal to 3, so it's not included. So its absolute value is bigger than 3 will get the same as this range. Or domain, I guess. What about this one? Well, this time it's the same thing, except that now we're looking for inclusive. So that means in between the minus 8 use your number lines in between the -8, which is here, and including, because it's the bigger or equal to sign, including all this in here all the way up to +8. Okay, well this time it's the absolute value of x is smaller or equal to 8. And no matter what value I plug in from in here, including the -8 and the +8, it will work because it's smaller or equal to. And anything outside the 9 or the -9 will not match this agreement. And therefore, absolute value smaller or equal to +8 is the same as this domain here. It's essentially just a domain that is balanced equally on either side. Okay, this is an interesting one, but it's the same thing really. We got smaller or equal to -1 or bigger or equal to 1. So on the number line, that's smaller or equal, so it's -1, including -1 all the way down here, and forever that way, and +1, and including +1 all the way up here, forever that way. That would just be absolute value of x is bigger or equal to 1. And you'll find that any value, for instance, if I put 0 in there, which should be not in the range, 0 is not bigger or equal to 1, so 0 does not work. And you can see that any other number will work and get me the numbers and the range, the domain I want. Oh, here's an interesting one. I didn't really think about this one. But I imagine you can just do the absolute value of x cannot equal 5. So it's saying plus or -5. So sure enough, if I put -5 in there, it gets absolute valued. It cannot equal 5. So therefore, -5 would not work, and 5 would not work, and everything else would work. Because -6 does not equal to 5. -7 does not equal to 5, etc., etc., etc. Once it becomes absolute value. Only the 5 and the -5 will make this not true. So that's all they're trying to get used to. Then they want you to reverse it. They want you to graph it on a number line. So notice the smaller than 8 means it's inclusive. So you should get used to the reverse as well. So it means not including, -8 all the way up to 8. But everything in between is what this is. And when it's bigger or equal, it's solid -16, solid 16, and it's everything outside of that. That's what the bigger than means. Okay, here's a smaller, and even though they use -4, oh, that's interesting, actually, smaller or equal to -4. I don't think that's possible, because there's no value I can stick in there that will ever be smaller or equal to -4. And then I believe this is supposed to be -1, and I just messed it up. Let's see. -7. It's supposed to be bigger than -7. So this last one's supposed to be -7. And so that means on the number line, and it's not including. Lots of things are bigger than -7. Actually, all numbers that are absolute valued are bigger than -7. So on that line, yeah, it would be circle there, and everything solid to the right. So actually every single number would still work, and so that would be everything except the -7. Because if I put -8 in there, it becomes +8, and it is indeed bigger than -7. The only number that doesn't work, oh no, even -7 works. So you can see that that is sort of a false. Whenever you have a minus number, it doesn't work at all, because every absolute value will be bigger than the minus number. And this won't work at all because none of the numbers will be bigger or smaller than -4. So that's just some weird. Again, I find this chapter sort of useless. So they want you to continue rewriting. So I'm just going to crop it, make a lot of space over here. Okay. So notice that this one's inclusive and includes the -3 and the +3. So that's going to be absolute value of x is smaller or equal to 3. And you'll find any value I fit into there will match this blue range when it's true. You can see that this one, the range is outside of -2 and 2. So that means absolute value of x is bigger, and they don't include the 2. That's what that circle, empty circle, means. Bigger than 2. You'll find that whatever I put in here, if I put a 0 in here, is not true. It will match this drawing here. So absolute value of x is bigger than 2. This one, they're including the 2. So the only thing that changes here is that I have to put an absolute value of x is bigger or equal to 2. And everything I plug into there will match this graph now. And finally, this is not including the 4 on the right or the left, but it's everything in between. So if the absolute value of x is smaller, not equals, because of the circle, than 4. And anything I plug in here for this to be true will indeed fall on this number line. Okay, they're asking you to graph some things. So let's just look at the graphs. This is simply a absolute value graph where all the values have been shifted to the right by 8. And this one, to properly show what's going on here, you have to factor out -1 here. So it's an absolute value of a minus, and when I factor out -1, I get x minus 8. So the only difference between this one, where everything has been shifted to the right, is that this one, everything's been shifted to the right, but then everything reflects in the y-axis. So if I'm going to graph it, 1 is going to look like this. It's going to look like a normal absolute value, except that the vertex is now at 8, 0, and it's going to go up 9, 1, 10, 2. And over here it's going to go 7, 1, 6, 2. So that's what that one's going to look like. And this one is going to have the same thing, so all the x values go to the right, but all the results are now negative. So it's a reflection in the y-axis. So it's the exact same graph except -8, 0, -7, 1, -6, 1, -9, 1, and -10, 1. So you can see that this one is that one reflected in the y-axis, and that's what that minus does. The only way you can really see it is when you properly factor out this middle. You're never supposed to have a minus in front of your x value. Your x values, to see the proper transformations, are supposed to be positive, which means I had to factor out this -1 to see that the x values are moved to the right by 8, but then they're all multiplied by -1, which makes them go over here. I think that's it. Let's use Desmos to verify that. So one is y is equal to the absolute value of x minus 8. So there it is. And then y is equal to the absolute value of -1 times x minus 8. And let's see if I did it wrong. Looks like I did it wrong, actually. Oh, yes, I know why. So the first thing I had to do was multiply all my x values by -1 first, and then add 8, which essentially means nothing changed. Nothing changed. If I'm going to write it the way they had it, it's minus x minus... Oh! Okay, hang on. Minus x plus 8, though. Yeah. So there we can see that nothing changed. And that's because I forgot that for when you're doing the translations, this minus must be, you must multiply all the x values by the minus first before adding the 8. In doing that, nothing has changed with the x values because they started off perfectly centered around the y-axis. So multiplying them by -1 did nothing to them before shifting them to the right by 8. And that's the difference. Even though the translation is written differently, the actual outcome is the same. How could you have predicted this? Oh, geez, you'd have to have a pretty good understanding of the graph. Even I screwed that up. I was expecting, only because I applied the transformations in the wrong order. If I thought for 2 seconds, I think I could have predicted it properly. Graph the following. Okay, let's just figure out what's going on with the transformations. This one is a absolute value that's shifted to the right by 2. This one is an absolute value that's shifted up by 2. This one is an absolute value that's shifted to the left by 2. So this one's to the right by 2. This one's up by 2. This is the left by 2. And this one is down by 2. So they're all different transformations. It all depends on where it happens. When it's inside the absolute value bracket, it's considered to be happening to x. When it's outside the absolute value bracket, it's happening to the y values. Much like all functions, when it's happening right to the x, it's affecting the x. Compared to the graphs you drew in 7, how could you use transformations to derive the graph of this? Okay, this whole thing, all the x values are going to shift to the right, to the left by 3 and down by 4. I guess they're just trying to show you how the transformations apply, no matter what function you're using. Predict what the graph of this would look like. Verify your answer using graphic technology. Okay, so as I said, it's still not factored correctly. You have to get the x with nothing in front of it. So factored to correctly, I factor out a 2, and I get x plus a half. That's what happens when I factor out a 2 from this and from that. So the actual transformation is this graph is moving to the left by a half, and then all the x values are not being multiplied by 2, but being multiplied by a half, because you have to figure out the reciprocal of that. So you're getting a horizontal compression by half, which means it's going to get skinnier as well as moving to the left by 2. We can confirm this by typing this exactly into Desmos and this exactly into Desmos. So here's the, was it +1? I think it was +1. Yeah. So you can see here's the new vertex, and it has indeed moved to the left by half. So I'm just going to show you what the regular one looks like so that you can also see the compression. See how much thinner the purple one is? That's because it's been compressed by half. Now let's do also the correctly factored version of it. So it's 2 times x plus a half. We should get the exact same graph. And we do. So it just shows that one is correctly factored so that you can see what exactly is going on. And just looking at this, you would not correctly have seen what was going on. You would have said, oh, it's moving 1 to the left and being compressed by half, which is not correct. It's being moved a half to the left and compressed by a half. And you can tell that by the vertex. That vertex went from 0, 0 to -0.5, 0. At least I predicted that one correctly. Okay, how about this one? Predict graphing technology. So it's the same issue. They also have it in the wrong order. So the correct order is this: minus absolute value 2x minus 5 plus 3. So there's 2 y values being affected. Everything's getting multiplied by -1, and then you've got to add 3 to everything. And then this is not factored correctly. So the correct factoring of that is 2, open brackets, x minus 5 over 2, absolute values, and then plus 3 and -1. So let's look at what's going on. So here's a graph. Here's the table of normal values, x, y. when it's minus 2, minus 1, 0, 1, 2. Y is 2, 1, 0, 1, 2. So all my y values must be multiplied by minus 1 and then add 3. So my new table of values is this. Do the y values, minus 1, then add 3. So that's minus 2 plus 3 is plus 1. That becomes minus 1 plus 3 becomes plus 2. That becomes 0 plus 3 plus 3. And that becomes 1 times minus 1 plus 2. So we can see that this here is going to be the vertex now. And then the last one, 2 times minus 1 plus 3 is plus 1. Okay, now all my x values are going to be multiplied by half, and then you must add 2.5 to it. A little bit more complicated. So a half is that, and add 2.5 to it, you get plus 1.5. The next one is negative a half, and then when you add 5.2 to it, you get 2. And the next one is nothing happens to the 0, but then you add 5.5 to it, which is 2.5, which should be the vertex. And then this next one, when you multiply by half, it's a half, and then when you add 5.5 to it, it's 3, and the last one's 3.5. So this should be 5 points on the graph, and that should be the vertex. So you can see that the whole thing shifted up by 3. It reflected in the x-axis. But because it shifted up by 3, these points here will be higher. And actually, okay, yeah, that's what it's going to look like. So if I was going to graph it, it would look like this. The vertex is going to be at 2.5, 3. Then it's going to be 2, 2, and 3, 2. Then it's going to be 3.5, 1, and 1.5, 1. And I believe it's going to hit the 0 at 1. I got the numbers a bit wrong, but 1, and at 4. So let's do a graph of this. So it's 3 minus, we'll do it the whole way, 3 minus the absolute value of 2x minus 5, was that it? Yep. Okay. Cool. There we go. Yeah, there's all the points, and yeah, 4, 0, and 1, 0. And there's the vertex just as predicted, and there's some of the points that we predicted. And that's what it looks like. Notice even if I write it in the correct order, and the correct factoring, that it's the same graph. And all these visually you can predict if you figure out the actual transformations. And your teacher's going to throw that at you a lot, because x is the only thing that you can make confusing about how it's transformed. Okay, let's see what else there is. I don't think there's much else in this chapter. No, that's it. Anyway, this is a great example where Desmos really comes in handy in predicting and helping you understand the properties of these functions. And these functions, very much you need to understand the transformations, because it's in both functions and it's in calculus. So they go through the basic functions again, the parent functions. You should relearn them, figure out 3 classic points on them, and figure out their asymptotes, figure out their ranges, their domains, their exclusions, and why all those graphs have the thing. You should also learn a couple new terms, interval of increase and decrease, and what makes an odd function, which is not what you would think is, what makes an even function, what makes a continuous function, what makes a discontinuous function. And that's all in 1.3. And as I said, the summary of everything, so they go through the ranges here. And they give you some tips, because later on they give you word puzzles for you to solve these things, and I hate the word puzzles for these things. I'd rather just study the parent functions on graphs, because in science that's actually what you're going to be using, is data and graphs. You're not going to have word puzzles. And then it summarizes it here, as always, and then it runs you through some examples. And here's some word puzzles, which I don't really think are useful. But that's 1.3.